So in previous lecture, I used this kind of equations where you have sum over these residues AK, BK, and CK, and these definitions to calculate beta lambda in terms of the A coefficients, and also a recursive relation among the A coefficients. And I'm not going to repeat that same argument. It was a small calculation. You can do the same thing for the mass coefficient, which is gamma m, which I'll call gamma m, and for also for z phi. So let me define those coefficients first, and then I will quote the results, which you have to prove by yourself using the same calculations, the calculational technique. So define gamma m to be limit epsilon to 0 mu over m mu times d m mu d mu, and then show that gamma m is given by half lambda dd lambda of b1 lambda, and then the recursion relation is bk plus 1 is equal to lambda bk lambda. So that is for the mass coefficient, and then for z phi, define gamma to be equal to limit epsilon to 0 half mu dd mu z phi of lambda mu, and then show that gamma of lambda is equal to minus half lambda dc1 lambda, and lambda dck plus 1 d lambda half ck So using these equations and the perturbation theory result for the lambda phi-fourth theory, using those results, one can discuss the flows of these coefficients, the mass flow of the mass parameter, and this has a relevance also, which we will interpret further, doing some further analysis. We will have an interpretation for this also, and we will see that it is like anomalous dimension per leg, external leg of a proper vertex, and that also flows with the coupling with the scale, and that flow is determined, the anomalous dimension flows, and that is determined by this equation. So let me now go into discussing the flow equation for the proper vertex. So this is called renormalization group equation. There is no group theory here. It is historically has been called renormalization group equation for gamma tilde of n, and we are considering M as scheme. So what we use is this equation, this third equation. So mu dd mu acting on this entire thing, and that has two parts. One is mu dd mu acting on this. Then since it's a total derivative, it can be one can use the chain rule to write it as sum of partial derivatives with respect to lambda and partial derivative with respect to m, and then partial derivative with respect to mu. Now this term partial derivative with respect to lambda will be multiplied by d mu dd mu of lambda, which is basically beta lambda. Similarly, gamma m that I just defined will appear as a coefficient of partial derivative with respect to m, and then there's a partial derivative with respect to mu. So mu dd mu acting on this will be broken down to three separate additive terms, and then mu dd mu acting on this term will have gamma involved. So there are these many terms. So let me write down the result directly because it's a simple argument. That is this equation called renormalization group equation for gamma tilde n. And this is the partial derivative term with respect to mu, and then beta lambda mu, partial derivative with respect to lambda, plus m gamma m of lambda mu, then partial derivative with respect to m minus n times gamma of lambda mu. This acting on gamma tilde n p lambda mu m mu equals 0. So this equation dictates how the endpoint vertex should flow with respect to the scale, and we can solve this equation using the method of characteristic. So what you do is to introduce a dimensionless scale S, introduce dimensionless scale S such that mu is replaced by S times mu. Basically, the reason is that mu can be kept fixed while S can be changed to slide the scale. Okay. So also you recognize the couplings as functions of S. So that mu is replaced by a function of mu as a function of S, lambda mu is replaced by lambda of S, which is by definition lambda of mu of S. M of mu is thought to be M of S, which is M of mu of S. Okay, and then beta lambda should be viewed as d s times d lambda ds. Gamma m lambda is s over ms times d ms ds, and mu s is equal to s times d mu s ds. Okay. Now with the boundary condition that lambda at s equal to 1 is given by lambda, m at s equal to 1 is given by m, and mu at s equal to 1 is given by mu. Because mu as a function of s, mu of s is nothing but s times mu. Okay. Then we could integrate this equation to write log s to be equal to integral d lambda prime over beta lambda prime lambda to lambda s. And this equation can be integrated to write m of s to be equal to m times exponential integral ds prime over s prime times gamma m of lambda s 1 to s. Okay. So s is playing the role of mu, and s is dimensionless, right? Then RG equation for gamma tilde n can be rewritten as all these partial derivatives with respect to lambda m and partial derivative with respect to mu, they are they are coming from mu dd mu, which gets converted into s dds minus n times gamma of lambda s, acting on gamma tilde n of p comma lambda s ms mu s equal to 0. And this equation can be integrated to write gamma tilde n p lambda s ms mu s to be equal to exponential n times ds prime over s prime 1 to s gamma of lambda s prime p lambda m mu. Okay. So lambda m mu are the values of lambda s ms mu s at s equal to 1. So this equation will solve this differential equation for an arbitrary value of s. Now the trick is to invert it. Let me invert this equation. Then I scale the mass parameter on the right hand side by s. So let me write and then explain. S to the power dn so p divided by s comma ms by s times mu s over s, which makes it mu. So what have I done? I have scaled all the mass parameters on the right hand side by a factor of s. So this is s times mu. When I scale it by s, it becomes mu. This is ms by s, and this p is replaced by p by s. Now, if I do that, then that would be wrong. This is not same as this, but it will become equal if I multiply this by s to the power dn, where dn is the mass dimension of this vertex. So this is engineering dimension of gamma tilde n, and that's dn is equal to d minus n times d by 2 minus 1, which is equal to 4 minus n. Okay. But now notice comparing this quantity on the left hand side and this on the right hand side, you are actually scaling the engineering or the kinematical quantities like p and m mass parameters by a factor of s, which is supposed to give you s to the power dn, but there is another contribution here, and you can interpret what that is if you take gamma to be constant. If you take gamma to be constant, then it will come out. So gamma comes out, it's minus n times gamma times log s, and that is same as s to the power minus n gamma. So this contribution, this factor, is s to the power minus n gamma for constant gamma. And that means that minus n times gamma of lambda s is a scale dependent quantum anomalous dimension. Because it is replacing dn by dn plus this additional contribution. So this is a scale dependent quantum and anomalous dimension. Gamma minus gamma is that per external leg. So that's the interpretation. Okay.